What's up, guys? This video is about integration by parts, which is in my opinion one of the harder integration techniques. Remember, what we're going for is that you'll be given some equation that you need to antiderive, and you'll have a list of integration techniques to try to use. Last video we learned U sub. This video is about integration by parts, IBP. Then you got trig integrals and trig substitutions, and then you got partial fraction decomposition. Talked about this technique last time, and we'll talk about these two in the future. The lesson you really want to learn from this whole integration techniques part of calculus is being systematic. You'll see some big equation you have to antiderive, and you should be able to look at that equation and think, alright, I'm going to try U sub on it. And if U sub doesn't work, okay, I'm going to try integration by parts on it. Or maybe instead partial fraction decomposition on it. You want to be systematic. You want to have this list of techniques in your head, and you want to know when to use each technique. You want to use trial by error. If each one of these guys doesn't work, you know it's going to have to be this one. You want to be as systematic as possible. That's the real lesson of this integration techniques chapter. So this video is a conceptual introduction to integration by parts. We'll do a simple example just to get the feel for it. I won't derive anything. I'll have the derivation for IBP in another video if you want to take a look at that. So before watching this video, you want to make sure you know U substitution. That's probably the most common integration technique. You'll use that all the time. And you want to make sure you know the product rule of differentiation. Just like U sub is the inverse, the undoing of chain rule, integration by parts is the undoing of product rule. So if you were asked to derive the following equation, you would do product rule on it, because you know that you use product rule when you see an equation y that's made up of two mini equations getting multiplied by each other. Well, that's generally what integration by parts is. So, integration by parts is in general used when two equations are getting multiplied. It is the inverse of product rule. But just know that there are plenty of scenarios out there where you can use integration by parts on just one equation. So just know that they're out there. So, this is the integration by parts recipe. This is what you'll follow whenever you're carrying out the integration by parts technique. This equation can be derived directly from product rule. We can really show how integration by parts is the reverse of product rule. And we can show where this equation comes from, but we won't do that in this video. We'll just show you how to use it. So, here's how this goes. This right here is the problem. So this guy and this guy are the same. You'll want to choose a u, and you'll want to choose a dv. You might choose your u equation to be x, which makes everything else dv. And what you're doing really is, once you choose your u and dv, you execute this right side of the equation. What you're doing really is you're transforming your tough integral into hopefully a much easier integral right here. And notice what this integral has. It has du in it, and it has v in it. You want to make your u choice such that its derivative is nice and simple, and you want to make your dv choice such that the antiderivative of this dv, that is v, is simple. So two things you'll want to abide by there. So let's solve this problem right here. So I want to take our problem and map it to a u and a dv. I want to make a u choice. That'll be the first step. and my dv choice will be my second step. Remember, we want to make our u choice so that its derivative is as simple as possible. We're on step 1 right here. I can either make my u the x, or I can make it the cosine. Well, which one has a simpler derivative? Because we're going to be dealing with that derivative in our second integral here, the one that hopefully will be easier than our current problem. So it's no contest, x has the most simplest derivative. It's just 1. So u is going to equal x. Now by default, that makes this remaining stuff my dv. We didn't really have to think through step 2 right here. But there are some cases where you'll have an equation where either u choice that you make results in an easy derivative. You can't tell which u choice to make from step 1, which means you need to let step 2 decide. You'll make your dv choice, and then the other equation will be the u. And just know that your dv choice has to include that dx. So here, the u choice is easy, so we don't really have to think about which dv to choose. Now the rest of my integration by parts recipe involves using the v as well as the du. So I've got to somehow get these symbols to arise. Well, the way to do that is to, let's take the derivative of my u. Well, derivative of u with respect to x, that's simply 1. And I know I want my du by itself because I want to substitute it. So du equals dx. There we go. Now I also want to get my v to appear. Well, how do I make the v appear? Well, take the antiderivative of both sides here. If I do that, I get a v on the left side, and the antiderivative of the cosine is going to be sine of 5x over 5. And I knew that so quickly because I'm an expert at u sub. I've gotten plenty of practice with u sub. I can basically do it in my head now. But just know that this step is a u sub step. So now I've assembled my v. So I've assembled everything. I have u, I have v, and I have du. So I'm all ready to crunch this right-hand side of the integration by parts recipe. So let's do that. So my problem, that is my left-hand side of the integration by parts recipe, will equal first my u, that's x, times my v, that's sine of 5x over 5. We got a minus sign, the integral, and here's my new integral, the one that hopefully will be easier. Otherwise, what's the point of all this? I got my v, sine of 5x over 5, times my du here, which is just dx, and there we go. I finished the integration by parts recipe. So this is my answer right here. The problem is my answer is not complete. I have to figure out this hopefully easy integral. And if you look at it, that is a pretty easy integral. That's just a u substitution. So the antiderivative of this guy is going to be negative cosine of 5x over 25. And of course a plus c. And again, I knew that because that's just a u sub right here. And I won't show the steps for that. So all I got to do now is simplify my answer. Just got to make sure I FOIL in that negative in correctly. So if I do that FOILing correctly, this term becomes a positive, and this technically is a negative c, but since this c is just a number, it doesn't really matter. The c is just a straight number. It could be negative, could be positive, could be anything. So this right here is my final answer. Okay, and that is it for this video. This was just meant as sort of a conceptual opening, a conceptual introduction to integration by parts. Let's just summarize real quick. Integration by parts is really the inverse of the product rule, and you can really derive this integration by parts recipe from the product rule, which I'll show in another video. And we talked about the general approach to using this recipe. That's these two steps here, 1 and 2. And we applied this recipe and these steps on a simple example. So I'll have some more videos where we use this integration by parts approach that we've developed on other problems. You definitely want to practice with this one. It is probably the hardest integration technique that you will learn.